Okay, this is the additional video for exercise chapter 14. And for the first problem, we have the problem within the 14.2, the limit on the function of two variables. So we have limit as x and y approach 0, 0, and with a different function, and we need to determine whether the statements are true or not. So there might be more than one answer for this question. Okay, you can pause the video and solve by yourself and check later with my solutions. Okay, now for statement A, so let me write limit as xy approaching 0, 0, xy squared and x squared plus y with power 4. Now to imagine this as a statement, we can take a look on when we have a different path, right? We can have a path of x equals 0, y equals 0, in which when we develop this, when we have x equals 0 and y is just y as a variable, then we will have 0. Okay, the result for the limit is 0. When we have y equals 0 and with variable x, we have also 0. It seems true, but if we check with y equal x, if we want to check, then perhaps this will be going to have limit as xy or the x become y, so y cubed, y squared plus y4. It seems not really a good approach, but if you look at how the structure of the functions, we have y squared, we have y4, we have x and x squared. So perhaps if we change x into something quadratic for y, so for example, if we have x equals some gradient y squared, or x equal y squared, if you would like y squared, then we will have, if we check with x equal my squared, then y equal to approaching 0, then this will be m y squared, y4. This will be m squared y4 plus y4, and I think we can cancel all y4, so we will have m over m squared plus 1, and m can be any number, so it's certainly not 0, so it's not equal 0, so the statement is false for number A, so this will be false. Okay. So certainly you need to imagine the structure for the functions, right? And imagine that if you can rearrange the structure and you can maybe eliminate one of the variables, I think that will be one way to think. Okay, another set of limit, we have this number b. Okay, we can write the limit as xy okay. Okay, what we have here is we have 3xy squared, x squared plus y squared. It seems if we check with the line x equals 0, y equals 0, we will have another 0, right? if we check through through the y squared, so 3m y4 m squared y4, I don't think this will be helpful because we have y squared. So if this happens, perhaps we can take the imagine that if we compare this structure and compare with another structure that easy to be followed, I think this is true, right? This is true. If we have this is true. And of course, this is actually 3 over x. So this also less than 3 absolute value x. So we can say that by squeeze theorem, because if we take the limit of the right function here, if you take the limit here, this would be 0, right? So limit this is 0, so this is true. Now the number c, so this will be a, b, we'll write c on here, okay? So limit as x, y going to 0, 0, x squared plus y squared, ln x squared plus y squared. Okay, now what we can do now? Okay, so first, if we imagine another functions as 0, I don't think we can have good results, right? So I think one way to solve this is by changing the Cartesians into parametric. That we can do. So change to parametric. We can also do this to help us to simplify the equations. So x will be r cosine theta, y will be r sine theta. So x squared plus y squared is become r squared, right? So we will have limit. So as x goes to 0 and y going to 0, r will be going to 0, right? So we can change the limit, and the expressions become r. So we have r squared ln and r squared, like that. Now what we can do here, we can set up the expressions as this is ln r, this is 1 over r, this is also ln r, 1 over r, like that. And since this part already 0, we don't need to calculate the other part. Well, it's actually another 0. So we can conclude that from the L'Hopital rule, okay, if we use L'Hopital rule to solve this, because it's infinite over infinite, so we can take the L'Hopital rule, this will be 1 over r, this will be -1 r squared. We can delete this and we have 0. Okay, so it's 0. So c is 0. It's true. Okay, now a last part. We got limit x, y, 0, 0, and we have sine x squared plus y squared, x squared plus y squared, and the same, I think same similar solutions that we can set up the parametric variable r. So we will have r going to be 0 sine r squared and then over r squared. I think this is with the definition of limit in sine r squared over r squared. This will be result, or I think we can just write in this just one line here. This is equal 1 by definition. By definition. So this is again true. So B, C, D is our answer. Okay, you can take notes and we'll go through another questions. Okay, now I have this another question. It's still about the chapter 14. Now specifically on the implicit partials. Okay, so we have functions. We have z as a function of two variables, and we would like to evaluate the partial z or dou z over dou x when xy is equal 0 and 1. So you can try this by yourself and you can compare the results with my solutions. Okay, the solutions. Okay, first, let me give you the first solutions that we have. Z is a function of two variable x, y, and we would like to derive with the respect of x. So we can write down the whole equations first, and then derive all with respect to x. So we are going to treat y as a constant and z as a function of x. Okay, so we will have 3 y z squared dou z dou x, and then plus we have a product rule now. We have a product rule. Let me go here. So first is 2x z squared plus 2x squared z dou z dou x, and then equal, we are going to have okay, so e derive become e, and then dou x. Let me write one by one, and let me solve this first. Okay, let me solve this. Becomes yz plus xy, and then dou z dou x. So it's quite formulations, right? Okay, we have 3yz squared dou z dou x plus 2xz squared, but I don't think it will be complicated if we are going to evaluate xy. So xy is 0, 1, and z is 1. So z is 1. So we can compute. So every x will be 0, 0, 0. This will be 0. So this will be 1. This will be 0. And the other one will be 1. So 1, 1, 3 equal 2, 1. So dou z dou x will be equal to 1 over 3. That will be the answer. Another steps that we might use is we can use the implicit formulations. So we are going to have partial x divided with partial z. Okay, now the partial x, or maybe let me write the functions again. the functions is yz cubed and the partial x is 2x squared minus yz e xyz. Partial z is 3 yz squared plus 2x squared z minus xy exyz. Okay, and we check with the we input all numbers 0 1 1 0 1 1. Now we have partial x is partial x, let's input, this will be 0, this will be 0, so will be -1, this is -1. Partial z will be this will be 3, so 0 and 0, so will be 3. So this will be negative, so it will be 1/3. Same answer. Okay, so you can have these two methods in your solutions. You can pick just one method that you feel it's more suitable for you. Okay, another additional questions. We have questions about the tangent plane equations. So we have a surface sine xyz and then x plus 2y plus 3z, and it goes through by this point. So we need to find the tangent plane equation. So you can try and pause the video and then look on how to get the tangent plane, and you can compare with my results, okay, at the end of the video. Okay, now first we need to set up the functions. Since we already learned on the gradient vector, so I think it will be very nice if we can set up the all the function. Oh, sorry, it's not x, it's x, y, z, and then we can set up the function as this one. Okay, so the whole thing from the beginning here, we are setting it as a function of 3 variables. Okay, now the next thing is we are trying to get the gradient vector. So gradient vector, we will have, first we are doing it for the x, so we will have cosine xyz and then yz, or maybe let me write yz at the beginning to avoid confusions. Okay, and then -1, and the other will be 0, and then partial, so this will be partial x, okay, to help you to distinguish from the others. So the other one, the partial y, we have cosine xz cosine xyz -2. So this will be the partial y, and the last one will be the partial z. This will be xy cosine xyz and then -3. And this is all the gradient vector of the function f. Okay, now we are inputting our point, which is 2, -1, and 0. So we are going to, because we have 0 here, so it's easy to make it 0. So we'll be having -1, and then another, if we have 0 here, then it will be 1, and this will be also 0. I think it's 0, the total 0, and then this will be -2, and this part will be this -2, 1, -2, -3, it's -5. So we have this for partial x, partial y, and partial z. As we know, this partial x, partial y upon partial z, oh sorry, this is not x, this is z. So all these partials will be our, we can treat all of those partials as our directions for the tangent plane. So we can set up the tangent plane. So tangent plane. So negative, negative 1. And then we can set up the x minus 2 for the point. And then minus 2, y plus 1. And then minus 5, z minus 0. So just z is equal 0. So we can set up the equations. 2 minus x minus 2y minus 2 minus 5z. Or we can simplify it. We can cancel this. We can simplify it and become x plus 2y plus 5z equal to 0. So this will be our answer for the tangent plane. Okay, next question. We have z as a function of two variables x, y, and we have x is s plus t and y is s minus t. And we have these relations, and the question is asking what is the scalar, or what is the these symbols for the one that is asking here, the square one. Okay, so to answer this question, we need to make our, at least understand how the connections between the chain rule for all functions. Okay, you can pause the video and try by yourself, and we can compare the results by the end of the video. Okay. Okay, I think we can start with because we have s and t, so we need to have a connections to get dou z dou s and dou z dou t, right? So if you are maybe not familiar, we can start by confirming with a tree diagram. So tree diagram, we can start with f or z. Okay, z or f, maybe z, just z. I think just okay, z. Z is having x and y, branches x, y, and x having s and t, y also having s and t. So we will have dou z dou s will be dou z dou x. Okay, and then dou z dou, oh sorry, dou x dou s plus dou z dou y dou s. Same thing with the t, dou z dou x and dou x dou t, and also dou z dou y and dou y dou t. Okay, now we can exchange all these symbols for partials with the actual functions. So x is s minus t. So we need to derive with respect to s first. So dou x dou s will be 1. Okay, and dou x dou t will be negative 1. Okay, and from y we have at, oh sorry, this will be plus, this is plus, sorry, for y is s minus t. So we have first is 1, and for it's not y, it's not x, it's y, sorry. This will be negative 1. So we can exchange all the terms. So dou z dou s is dou z dou x, and then the dou x dou s is 1, dou y dou s is 1. So we have this. Okay, and then we have dou z dou t. This is dou z dou t 1, dou z dou x minus dou z dou y. Okay, Okay, so to make these connections, we see that in our question here, let me erase this first. We have this multiplication. So let's multiply, and I think because we have seen that we have plus and minus, and we have the same symbols, we can treat this as in a plus b multiply a minus b, which results in a squared minus b squared, right? So if we multiply dou z dou s multiply with dou z dou t, this will result in dou z dou x squared and then minus dou z dou y squared. So the question is asking what is this number? So it should be -1. So it's A. Okay, I hope you get the point. Okay, so I think this part is the key. The diagram is the key. So whenever you have confusion on the chain rule on the partial derivative, I think it's better to use this schematics on tree diagram. It will be helpful to help you get through some of the problems regarding the chain rule. Okay, I think that's all for this additional video, and hopefully this will be beneficial for your study.